Hello and welcome back. In 7.3 we start looking at extrema. Again, in the context of multiple variables. So we'll start with a theorem. So theorem 1, we're going to let f of AB be a local extremum of f. So we have this 3D surface, and at x equals a and y equals b, we have a either highest point in a neighborhood or lowest point in a neighborhood. If partial derivative of x and partial derivative of y exist at AB, then each of those partial derivatives is 0. One little note on this, the converse is not true. i.e. saying partial of x equals 0, partial of y equals 0. That does not guarantee an extrema. So in other words, it's a necessary condition but not sufficient to prove it. So let's start with this. So we're going to find partial of f with respect to variable x, partial with respect to y, and we're going to use theorem 1 to prove, sometimes they'll say show, there are no local extrema. And finally our function, so what we're working with, f of xy is going to be 24 minus 4 times x minus 7 times y plus 2y squared. So we have this multivariable function. We want to use theorem 1 to show that we don't have any highest or lowest points on this. So this is sort of the 3D version of, for example, just the identity function y equals x. We have no highest or lowest point on that. No matter what point you identify, I can find a point near it that's lower than it, and I can find a point near it that's higher than it, no matter how small you make this interval. So it's the same idea here, except again, instead of working on a flat plane, we're working in three-dimensional space. So first let's find our partial derivatives. So with respect to x, 24 always has a 0 derivative since that's a constant. Derivative of negative 4x is negative 4. Derivative of negative 7y when we're differentiating with respect to x is 0. Same thing with the last term. Our partial with respect to y, first two terms 0 out because they're either one is a constant, the other is treated as if it were a constant. So we're just differentiating these last two terms. So we have a negative 7 and we have a plus 4y. So theorem 1 says that if there is a local extrema on this graph somewhere, that each of those partial derivatives has to be worth 0, but -4 cannot equal 0. Therefore, there does not exist. So a little side note there on my notation. Backwards capital E is shorthand in math for there exists, with the slash through it. There does not exist. So we don't have any extrema on this graph, since our partial with respect to x is never going to be able to equal 0. We could find a place where partial with respect to y is 0, but we can't do it with the x. So that's our theorem 1. It says that if there is an extrema, both partials are worth 0 at that point. Theorem 2 gets into how to identify an extrema if we have it. So we're going to let z equal our f of xy, our multivariable function. Further, that partial with respect to x at point AB is 0, as is the partial with respect to y at point AB. All three of our possible second derivatives exist, at least in a circular region around AB. And we're going to do a few definitions. So cap A is going to be our second partial derivative with respect to x each time at point AB. Cap B, partial with respect to x and y at point AB. And point C, partial with respect to y both times, again at point AB. So if we have all of these conditions, then, and theorem 2, I'm not going to ask you to memorize it. I'm going to write it down for you and ask you to put it to work. I'm not going to ask that you memorize these cases. So case 1, AC minus B squared is positive. And, so remember with an and, a conjunction, both conditions have to be true. A is negative, and f of AB is a local max. Case 2, AC minus B squared is still positive, but A is also positive. F of AB is a local min. Case 3, AC minus B squared is less than 0. F of AB is a saddle point. Saddle point, think of Pringles. That oddly shaped potato chip. The center of the Pringles potato chip, if you look in one direction, it's the highest point on it, but at that same point on the potato chip, it's also the lowest point looking from the other way, so that would be a saddle point. So a Pringle point, if you will. So it's neither the highest nor the lowest. And case number 4, AC minus B squared is, the only thing we haven't covered is actually equal to 0. Test is inconclusive. So you would just need other means to test it. All right, so we'll look at just a few examples. So we'll start with f of xy being x squared minus 4 times x times y plus 2 times y minus 6. So first I'll start with the first derivatives. So partial with respect to x. So that would be a 2x and a minus 4y. Last two terms zero out. Remember, x is the variable, y gets treated as if it were just a number. We'll also differentiate the original with respect to y. So that means this first term zeroes out now. Second term, negative 4x. Come out of it since the derivative of y is a 1. Third term, derivative of 2y is positive 2, and derivative of a constant is always 0. So if I'm looking for local extrema, if they exist, I know that partial at AB of both the x and y have to be worth 0. So I just set up a little system here. So this would be a little 2x2 system. So the 2x minus 4y would have to equal 0, and the negative 4x plus 2 would also equal 0. So this one, you're solving a 2x2 system, so we'll double both sides of equation 1. So 4x minus 8y is worth 0, together with equation 2, just a little rearranging, moving the constant to the other side. And that was a negative 4x, so negative 8y is worth negative 2, so y is positive 1/4. And then we can do a little substitution to find our x value. So 2x minus 4 times 1/4 is 0, so 2x is worth 1. So 4 times a fourth is 1. A minus 1 here is the same as a plus 1 over there, so x is a half. So if we have an extrema, and we haven't shown that we do yet, if there exists an extrema, it is at half and 1/4. So to see if we do, continuing up here, we need our second derivatives. So second derivative with respect to x both times be a positive 2. With respect to the x, then the y would have a negative 4. Notice we would get the same thing if we had accidentally reversed the order on that. If we looked at this one and then differentiated with respect to x, we still get the negative 4. And of course, we'll also need, with respect to y both times, fyy of xy would be 0 here. So ffx at 0.1/2 1/4. I don't have any x's or y's to plug in, it would stay at 2. And the same thing will happen with xy at 1/2 1/4. I don't have any x's or y's on the right hand side to plug in. I'll get a negative 4 out of it. So that's our Alpha, Bravo, and Charlie. So then I find AC minus B squared. So that would be 2 times 0 minus negative 4 quantity squared. So AC minus B squared. 0 minus 16 is negative 16. That is less than 0. And if you'll recall from the previous page, if AC minus B squared is less than 0, it doesn't matter to us what's happening with anything else. We know that this is a saddle point. Similar problem. Again, same goal as the previous problem, new function. So x natural log y minus y plus 2. So we'll use our first partial derivatives to locate a possible extrema. Then the second will tell us if we actually have it there. So x is treated as if it's a variable. Natural log of y then would just be a constant. So this first term then would be linear. Derivative of a linear is just the constant coefficient. So natural log y. And next two terms drop out. Partial with respect to y. Now x gets treated as if it were just a number, and derivative of natural log of y is 1 over y. So x times 1 over y would just be x over y. Derivative of negative 1y with respect to y is negative 1. And last term drops off, as always. So I'll set up my little thing here to find my points, and then we'll go into our second derivative stuff as well. So I want natural log of y to equal 0. I also want x over y minus 1 to equal 0. So this one, as you can see, this is a nonlinear system. So substitution is really our only option at this one. So solving the first one, since it only has one variable in it, so natural log of y equals 0, so then e to the 0 is equal to y, so that's just using the properties of logarithm, turning it back into an exponential. E to the 0 is 1, so y equals 1. Then we sub that into equation 2, so x over 1 minus 1 is equal to 0. So x divided by 1 is just x, so x minus 1 is 0, x is a positive 1. So 1, 1, if we have an extrema, it's at 1, 1. And we get into our second derivatives and see if it's a local max, a local min, a saddle point, or if the test will fail us. So our second derivative, with respect to x both times, you should be able to tell that that's a 0 since we have no x's left there. Partial, one variable at a time. Derivative with respect to y of natural log of y is 1 over y. Notice that does match what we would get if we looked at this one and differentiated with respect to x the next time. We would still get a 1 over y. And then we'll do our partial with respect to y twice. So this would be, let me take a moment to make this a little bit easier on us. Partial with respect to y of xy. One other way we could note it is xy to the negative first minus 1. So then we're just using our friend the power rule. So x times -1 is minus x. Y is now to the -2nd. Derivative of a constant is 0. If you like it without the negative exponent, opposite of x over y squared also works for us. Okay, so now we plug our 0.11 into these guys. So f sub xx at 1, 1 is just going to be a 0. There's nowhere to put in any x's or y's. Partial with respect to each variable would be 1 over 1, which is 1. And y twice at 1, 1 would be opposite of 1 over 1 squared, which is a -1. So that's our Alpha, Bravo, and Charlie. So then we find AC minus B squared. Again, you don't have to memorize the AC minus B squared thing and what sign you're looking for. You're just expected to be able to put it to work for us. So AC minus B squared for this guy would be 0 times 1 minus -1 quantity squared. So AC minus B squared, again, is a negative. So that tells us we have a saddle point. Yeah, 1, 1. Previous saddle points, I don't think I remembered to identify it. It was at 1/2, 1/4. You identify where your saddle points are. Okay, so same goal, new collection, so x to the 4th plus y to the 4th minus 4 times xy. So go ahead and find both first partial derivatives. Go ahead and pause it, find those first partial derivatives. Welcome back. Partial with respect to x, 4x cubed minus 4 times y, so the y to the 4th, when we're differentiating with respect to x, drops out. Here, y is treated like it's a number, so the -4 and the y get treated the same. Derivative of a first power is a constant. So your partial with respect to y of xy, first term would drop off, then second term 4y cubed, last term minus a 4x. So then we make our little system here that if we have an extreme point, it's going to happen where each of these is a 0. So we'll just do a little substitution on this one. So using equation 1, 4y is worth 4x cubed. So y is x cubed, and we'll sub that into equation 2. So we have 4 times x cubed cubed. So the y got replaced. Minus 4x is equal to 0. So we have 4 x to the 9th minus 4x equals 0. We can factor a 4x. So 4x by x to the 4th plus 1 by x to the 4th minus 1. And that's still equal to 0. Still 0. And one more little bit of factoring we can do. Okay, so either x is 0 from that one. This one, we would have imaginary roots. For both that one and that one. And we're looking in, just like in the two-dimensional graphs where your x and y axes are number lines, three-dimensional graphs, the vertical one is still just a real number line. So if it kicks us out into the imaginaries, we don't want to attempt to plot that in the real plane. So x equals -1 from that factor, x equals +1, and then we put those back in and find our ordered pairs. So if y is x cubed, y equals 0 cubed, y equals 0. So 0, 0 is one of our locations that we'll test out. If I try out the -1, y equals -1 quantity cubed, y equals -1. So -1, -1 we'll try out as well, and trying out the 1, we also get a 1 returned. So we actually would run that test 3 separate times. So f sub xx, we'll start with the 0, 0. And we didn't calculate those just yet. Let's actually find them. My apologies. F sub xx of xy. So here's our partial with respect to x. We'll do it with respect to x again. So that is a12x squared. Second term drops. One of each would give us a -4 no matter what. And the y twice. We go to this guy, differentiate with respect to y again, 12y squared. So we try out f sub xx at, as I said, 0, 0. That would be a 0. F sub xy at 0, 0 would always be a -4. And f sub yy at 0, 0. 12 times 0 squared is also 0. So for that guy, AC minus B squared. There's our Alpha, Bravo, and our Charlie. 0 times 0 minus -4 squared is -16, less than 0, so a saddle point at 0, 0. If you wanted the z value as well, just plug it into the original. Then we have a new set of A, B, and C's for -1, -1. So 12 times -1 squared is +12. That's our new A. One of each at -1, -1 is always a -4. That's our B. And the y twice at -1, -1. 12 times -1 squared is 12. That's our C. So AC minus B squared this time is 12 by 12 minus -4 squared. So AC minus B squared, $144 minus 16 is definitely greater than 0. So then I want to know then the second part of our test. So I want to know if A is greater than 0 or less than 0. So A here, A was 12, which is greater than 0. So this is a case 2. So that means f of -1, -1 is a minimum, local minimum. And then we can finish it off with the ones. So f sub xx at 1, 1 is 12. F of sub xy at 1, 1 is the negative 4 no matter what. That's our b. 12's our a. Sub yy at 1, 1. 12 times 1 squared is still 12. That's our c. So we have the same a, b, and c again that we had before. 12, negative 4, and 12 again. So this time we see the same conditions that we saw on the negative 1, 1. So 1, 1 is a local min. All right, so we do have a couple of word problems to cover. We're going to cover those next time. So I'm going to give you the full assignment and ask you to wait on the word problems. So this is from section 7.3. So we're just looking at part 1 at the moment. So 9 through 33 odd, 43, 47, and 49. Again, for now, skip word problems. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.